This is lesson 3-5, proportions and similar figures. Similar figures are figures that have the same shape, but not necessarily the same size. Think of going to the photocopier and either enlarging something or reducing it in size. The shape would be the same, but the size would not. For example, let's just say I have this triangle here, and I have a triangle that's just a little bit bigger than that triangle. In either case, these are what we call similar figures because they're both triangles, they're just different sizes. A dilation is a transformation in which a figure and its image are similar. This figure over here, the larger triangle over here, would be a dilation of the smaller triangle. That is a dilation of the smaller triangle. A scale factor is the ratio of the dimensions of the new image to the dimensions of the original image. We'll talk a little bit more about that when we get to a figure that we're actually going to look at. A scale drawing is an enlargement or a reduced drawing that is similar to the actual object or place. If you've ever created a model airplane or a model car, that's actually what we call a scale drawing. It's smaller than the actual real car because if you had a real car and you were building it to actual dimensions, it would be a car when you were done. When you build a model, sometimes the scale is sometimes 1/64th, which means 1 inch on the model is 64 inches in real life. The scale is the ratio of the distance in the drawing to the corresponding actual distance. Like I said, 1 inch to 64 would be, 1 to 64 would be like saying 1 inch is actually equal to 64 real inches. All right, let's take a look at these two figures here. In similar triangles, corresponding angles are congruent and corresponding sides are in proportion. For all similar figures, all the corresponding angles, corresponding means angles that match up, are congruent, which means they're equal, and corresponding sides, sides that match up, are in proportion. So if we look at this lovely figure here, if I was to tell you that triangle ABC here, or let's just call it CBA, if I said triangle CBA is similar to the other triangle, I would want to make sure that I get it in the right order. I'm going to tell you that it's similar, and the symbol for similar looks like a sideways S or half of the infinity symbol. CBA is similar to triangle EFB. That tells us that angle C matches up with angle E. These have to be the same measure. Angle B matches up with angle F, so these angles have to be the same measure. And last but not least, angle A has to correspond to angle D. Angle A here corresponds to angle D over here. Now, if I told you some measurements of this triangle, okay, let's say I said measurements such as 8, 10, and 12. If this is 8, this is 10, and this is 12. And on my other triangle, I'm going to tell you 12, 15, and 18. 12 here, 15 here, and 18 here. In order for these two triangles to be similar triangles, the corresponding angles must match up. We have the corresponding angles matching up. Angle C is congruent to angle E. Angle B is congruent, and that's the congruency symbol, an equal sign with the partial infinity sign or the similar sign. Angle B is congruent to angle F. And last but not least, angle A is congruent to angle D. That part matches up. So we have corresponding angles are congruent. Now we need to see if the corresponding sides are in proportion. To see if the corresponding sides are in proportion, we have to have the corresponding sides. So if we were to look at this figure for a second, my corresponding sides, CB here, side CB here corresponds to side FE. So if I have CB, which is a line segment, corresponds to EF. Okay. Now let's look at those proportions. Let's look at those ratios. That's in a ratio of 8 to 12, or as a fraction, 8 over 12. We can reduce that. 4 goes into 8 twice, and 4 goes into 12 3 times. It's a 2 to 3 ratio. If this triangle were to stay in proportion, all of the corresponding sides would have to be in the same proportion. So we already have those two sides. Let's take a look at another set of sides. Let's take a look at B to A, and that has to correspond to F to B. Okay, so BA corresponds, I'm going to abbreviate that, to FB. And BA is 10, FD is 15. When we reduce it, that's also in a 2 to 3 ratio. So far, so good. 2 out of 3 sides are in the right ratio. And let's look at the last set of sides. That would be side C to A, and that corresponds to B to B. Right. So let me highlight this really quickly. So we have that. So we're going to have C to A and F to B. And so CA corresponds to EB. Okay, and that side is 12, and FEB is 18, and 6 goes into 12 twice, and 6 goes into 18 3 times. So you can clearly see that all 3 of these are in the same proportion. Okay, 2/3, 2/3, and 2/3, which means that these figures are similar because the corresponding angles are congruent or equal, and the corresponding sides are in proportion. Now, how does that help us? Well, what's really cool is now if we're missing parts to a triangle, we just need to simply set up a proportion and solve. For example, if we look at this triangle ABC, okay, and it would be A, B, C, and there should be an F up here. I don't know where F went. So the triangles are similar. And I'm going to tell you right now, triangle A, B, C is similar to triangle. And you have to keep these in the right order. I went from A to B, and then B to C. So I'm going to have to go D to F, and then F to E. So that would be triangle D, F, E. So those are my similar triangles, which means my corresponding sides must be in proportion. So if they're similar, that means this side here should be in proportion to that side there. So let's look and see if this, so we can solve the smaller triangle side 6 corresponds to the bigger triangle side 9. The smaller triangle side 8 corresponds to the larger triangle side X. So 8 over X. We now have a nice little proportion here. 6 over 9 equals 8 over X. We simply need to cross multiply to solve, and then we cross multiplied a couple of lessons ago. So 6X equals 9 times 8. 6X, 9 times 8 is 72. If we take 72 and divide it by 6, you are going to get 12. So X equals 12. And if you remember way back up here, and I'll move it back up, it was labeled in centimeters, so we should probably label it in centimeters as well. And there you have it. You can solve for a missing part. Once you know that you have similar triangles, you just set up proportions. Now, you can also use proportions to find dimensions of objects that are difficult to measure directly, like trees, for example. It's really, really hard to climb up to the top of a tree and drop a yardstick or a measuring stick or even a tape measure for that matter to figure out how tall the tree is. The tree gets skinny at the top, you're going to fall down, and I don't think there's going to be too many firefighters that are going to allow you to borrow their ladder truck just so you can measure how tall a tree is. So what we do is we create similar triangles by measuring things what we call indirectly. To measure indirectly, we're just going to simply draw some pictures. And I'm not very good at drawing pictures, so please bear with my ugly looking pictures. A tree casts a 26-foot shadow. Okay, so here's my tree. Isn't it lovely? Okay, sun must be over here if it's casting a shadow that's going this way. Say the shadow is 26 feet. A boy standing nearby, and I'm really good at the stick figures. Here's my boy standing nearby. He had a smiling face on. He casts a 12-foot shadow. Okay. His height is 4.5 feet. He's 4.5 feet tall. How tall is a tree? We don't know how tall the tree is, so we'll call that H. if you notice, we can create similar triangles because the tree should be perpendicular to the ground, so create a right angle, and the boy should be perpendicular to the ground. I don't know too many people who lean when they're standing, so we can figure out how tall this tree is by setting up a proportion. Okay. The height of the tree, h, over the height of the boy, 4.5, equals the shadow of the tree, 26, over the shadow of the boy, 12. So there's our proportion. You could also set it up, the height of the tree, h, over the shadow of the tree, 26, equals the height of the boy, 4.5, over the shadow of the boy, 12. Because in both cases, you'll notice, you're going to still multiply h times 12 and h times 12, and you're still going to multiply 26 times 4.5 and 26 times 1.5. Just be consistent. If you're going to go tree's height to tree's length, don't go boy's length to boy's height. You have to go height to height, length to length, or height, or you just can't do height to length, length to height. It will mess everything up. You'll get really funny looking proportions. So if we're going to solve this, it doesn't matter which proportion I solve, I'm going to have 12h equals 26 times 4.5. Let me grab my calculator really quick. 26 times 4.5 is 117. So if I take 117 and divide it by 12, h will equal 9.75 feet. So it's not a very tall tree. Okay. So since this is a word problem, we should write it in a complete sentence. So the tree is 9.75 feet tall. Now let's look at another problem. Flagpoles. Flagpoles are kind of hard to climb up because they're metal or slippery. So if I have a flagpole, flagpole casts a 102-foot shadow, a man 6 feet tall casts a 17-foot shadow. How tall is the flagpole? Okay, so here we are. Here's my flagpole. Okay, it's going to cast a 102-foot shadow. And I have a man over here who's 6 feet tall. He's 6 feet tall here. He's going to cast a 17-foot shadow. So we need to know how tall this flagpole is. So we're going to create some little triangles here, just like this. So the height of the flagpole over the height of the man equals the length of the shadow of the flagpole over the length of the shadow of the man. Okay? Pole to man, pole to man. Okay, make sure you're consistent with that. So now when we cross multiply, 17h equals 102 times 6, which is 612. Divide by 17. And h equals 36 feet. So the flagpole is 36 feet tall. There we go. Now, we can also do scales here. When we're working with scale models, you just need to make sure that you're keeping your map scales accurate. The scale of a map is 1 inch is equal to 10 miles. That's right here, 1 inch to 10 miles. The distance from Grace to Vaughn is 2.25 inches. How far is the actual distance? Okay, so we're going, whoops, that was a mistake. Erase that. We're going inches to miles. So we just need to make sure we're consistent. So 1 inch is equal to 10 miles, inches to miles. The distance from Grace to Vaughn is given in inches, so that's going to go on the top. 2.25 inches is equal to how many miles? So we simply just need to cross multiply, so x is going to equal 10 times 2.25. So x is going to equal 225 miles. That one was fairly simple because it wasn't a hard conversion. 22.5, I can put my decimal point here. 22.5 miles. It wasn't a hard calculation to do. All right, so the actual distance is 22.5 miles. Okay, that one is if they give you the inches and they ask you to find the actual. You can do the other way around too. Just make sure you're consistent. The scale of a map is 1 inch is equal to 5 miles. So we're still going inches to miles. 1 inch is equal to 5 miles. The actual distance is 17.5 miles. Since it's miles, that goes on the bottom, doesn't it? 17.5 miles. We need to know the map distance, which is x. Again, you're going to cross multiply. 5 times x equals 17.5 divided by 5. 17.5 divided by 5. X is going to equal 3.5. And since 3.5 was up here on the top, which was the inches, we'll label it in inches. And of course, we should put it in a complete sentence. The map distance is 3.5 inches. We should have done that with the problem before it, too. Thus ends this lesson.